So translation look-aside buffer is a special cache inside a processor that stores the page number to frame number mappings of frequently used pages. Translation look-aside buffer is kind of a cache. So it is basically a fully associative cache. Okay. And every entry contains the page number and its corresponding frame number and some extra bits. Extra bits are status bits. We don't have to discuss about the status bits right now because we will only discuss how this TLB is used. Page number and frame number of frequently used blocks. Okay. Now let's see how it is improving the performance. So if I have a process P1, it generates a virtual address. Okay. So virtual address has two parts. One is the page number, another is offset. Now this goes to memory management unit. What this memory management unit does, the first thing is it will access the translation look-aside buffer. It will access this cache. It will see if this page number, this particular page number, its mapping is present here in the cache. So it will search this cache. If there is a mapping available in the cache, it will get its corresponding frame number. Okay. So from the TLB, it will see if this page number mapping is there. If it is there, so there are two possibilities, hit and miss. Miss means that, hit means that the frame number corresponding to this page number, that mapping is present in the cache. So if it is present, it will get the frame number, and to this frame number it will add the offset, and this will be our physical address. Then it will access the memory. So in this particular scenario, in this one, how many times we have to access the memory to get the data? Only one time. Now let's say this particular format. So let's say TLB and there is a miss. Miss means that the mapping of this page number is or this page is not in the TLB. Okay, so it will be a TLB miss. So in TLB miss, so that means now it has to convert this page number into frame number. That means it has to access page table, because in the page table there will be the mapping. So from this page table it will get the page number, and it will update this particular TLB with this new mapping, page number to frame number. Okay, so it will update TLB. So to this frame number it will also add offset to get the physical address, and then it will again access the memory. So in this particular scenario you can see that there are total 2 memory accesses. So having a TLB, we can decrease those extra memory accesses, but the only one thing we have to keep in mind, that hit rate should be very high. Now the question arises is that, do we have translation look-aside buffer entries for every process, or we can say at a time, are there multiple entries for multiple processes, or all the entries are belonging to a single process? So if my P1 is running, process P1, then the entries in the TLB at that particular point all belong to process P1. Now if I am moving context to switching to another process, I will flush these entries and I will update these entries with the entries of process P2 from its page table. Okay, so that means at one particular point of time, the entries contained in the TLB belong to one particular process. And if we are making a context switch, then we have to flush the TLB and update it with new entries. However, in some scenarios, the TLB is not flushed. What does that mean? It means that the entry may belong to any process. For example, this entry may belong to P1, this entry may belong to P2. But how do we know which entry belongs to which process? So with every entry, we add another important information here that is called address specific identifier. And that address specific identifier says to which process this particular entry belongs. And in that particular scenario, when we are making a context to switch, we don't have to flush the TLB. Okay, so this is all about the TLB and how it is useful in improving the performance in case of accessing the memory.